So let's do a practical example now where we talk about the step-by-step process of interpreting a proton NMR spectra. So in this case, we're asked to identify the structure of a compound with the molecular formula C9H10O given the following NMR spectra. So first things first, let's calculate the degree of unsaturation. This gives us a ballpark for what functional groups are present in our molecule. So we have a DU value of 10 over 2, which is 5. So that tells us that most likely we're going to have some sort of benzene ring or other aryl system. Next, we're going to note the chemical shift and integration of each signal and identify potential functional groups based on the chemical shift, integration, and formula. For example, this proton, proton A, is in the chemical shift value of 10, and it integrates for 1 hydrogen. So this could be either an aldehyde or a carboxylic acid. Given the chemical shift value and the fact that we only have 1 oxygen in the formula, we're going to assign proton A as an aldehyde fragment. Next, looking at proton B, chemical shift value around 7.2, and this integrates for 5 hydrogens. 7.2 indicates that we have an aryl proton, and the integration of 5 tells us that we have 5 aryl protons. Okay, now let's think about this fragment here. So chemical shift of around 3 part per million integrates for 2 hydrogens, and it's a triplet, which tells us N is equal to 2. We have a second integrated for 2 hydrogen chemical shift of about 2.8, and we have a triplet with N equals 2. So based on the multiplicity, these two protons are adjacent to one another. Now, in terms of the identity of those protons, a chemical shift of around 3 part per million, that could be one moment. So in terms of this chemical shift of around 3 part per million, we could very easily assign that to likely be a pair of 2 protons that are adjacent to an aldehyde. So this is our first fragment. In terms of the second fragment with the chemical shift value of around 2.8, that could be a pair of protons that are adjacent to the aromatic ring, these benzylic protons. I'll label these as proton D, while the protons adjacent to the aldehyde I'll label as proton group C. Okay, so we've noted the chemical shift values, we've noted the integration and multiplicity, and we've drawn some reasonable fragments that would match the given chemical shift and integration. So again, in terms of noting unique chemical shifts, chemical shift of 10 with an integration of 1, that's likely an aldehyde. Chemical shift of around 7, integration of 5 hydrogens, that's likely an aryl ring with 5 hydrogens. Chemical shift of around 3.2 with an integration of 2 hydrogens, that's likely the pair of protons adjacent to the aldehyde. Chemical shift of around 2.8, those are likely the 2 protons that are adjacent to our aromatic ring, our 2 benzylic protons. So based on the integration and chemical shift for each signal, we draw a structure fragment matching the chemical shift and integration for that peak. We repeat this process for as many peaks as possible. As you can see, we've already drawn out our fragments. So let's now take those fragments and let's see what we can do with those fragments. So again, we have this proton corresponding to the aldehyde, this set of 5 protons corresponding to our aryl ring. This set of protons, that's a triplet that integrates for two hydrogens, corresponds to the proton adjacent to our aldehyde carbonyl. And this proton set here corresponds to a pair of two hydrogens that are a triplet, and these hydrogens are adjacent to our aryl ring. Now, this is a key way that we put together our fragments, and this is very important. Based on the splitting pattern, we can identify the number of adjacent protons and how those protons are grouped. We can identify the number of adjacent protons responsible for the splitting pattern. For example, the peak at 3.2 that integrates for two hydrogens, that's a triplet, that tells us n equals 2. There are two adjacent protons. This can be related to our second peak that has a chemical shift of 2.8, integrates for two hydrogens, that's a triplet, which implies there are two adjacent protons. As we can see, these two signals integrate for two hydrogens and are triplets, implying this set of protons has two adjacent hydrogens, and this set of protons has two adjacent hydrogens. Thus, based on the splitting pattern, we can assume that this set of protons are adjacent. You can also see that by virtue of the fact that the J values look similar. The spacing between peaks as a result of splitting looks very similar for these two proton sets. You also see this kind of peak slanting effect. This is often a subtle signpost that a set of proton signals are coupled. Okay, so now that we've identified that these two proton groups are adjacent, what we're going to do is we're going to draw a structure fragment containing the correct number of protons to give the splitting pattern, and we're going to connect these structure fragments together. So for example, in order for this two hydrogen signal to be split into a triplet, we are going to draw it adjacent to another two hydrogen signal, and this gives the triplet-triplet splitting pattern that we've observed. So we drew out our fragments, and then what we've done is we've connected our fragments together in order to give the desired splitting pattern. Okay. From here, you can estimate the coupling constants visually and check the reported coupling constants. Protons with the same coupling constants are likely adjacent protons. As we've discussed, the spacing and coupling constant for these splitting for this peak on the left and this peak on the right are identical. The spacing of splitting and thus the coupling constants for these two peaks are identical. Thus, these two peaks are likely coupled proton peaks. These two sets of protons are adjacent and thus coupled. Okay, now we've drawn out a reasonable structure. Let's just make sure that everything checks out. So we have proton A for the aldehyde, proton B for our aryl protons, proton C corresponding to the protons adjacent to the aldehyde, and proton set D corresponding to the benzylic protons. Overall, this yields the following structure after we put together our fragments. Just to make sure, for proton B, we have 5 protons with a chemical shift of around 7.2. These are multiplets as a result of the aryl group protons engaging in splitting with one another. Proton A with a chemical shift of around 9.8 corresponds to the aldehyde proton. It exists as a singlet, but if you had a high resolution instrument, you'd actually see this peak start to split a little bit. Likely the instrument that they took this spectra on is a little bit of a lower end instrument, though aldehyde splitting is pretty hard to see because the coupling constant's only anywhere between 0 and 2 part per million. Or sorry, zero, the coupling constant is around 0 to 2 hertz. And so you're not going to really see a large part per million difference in terms of splitting. Okay, let's take a look at now the protons adjacent to the aldehyde, proton C. These have a chemical shift of around 3.0. We integrate for two hydrogens and they're a triplet. So there must be two adjacent protons. And we in fact can see those two adjacent protons. The two adjacent protons that are causing this splitting pattern are proton D, which integrate for two hydrogens, which explains the observed multiplicity, and they have the chemical shift of around 2.8, and they're also a triplet. What's causing that splitting? The coupling between these adjacent pairs of two protons each. Okay, so we've drawn out our structure and we verified the chemical shift and splitting patterns for the proposed structure matches the NMR spectra. One other check that you want to do is to check the DU value. This has a DU value of 5, which matches our calculated DU. And our formula in this case was C9H10O. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and 1 oxygen. So everything checks out in terms of the DU formula, the peak chemical shift, the peak integration, and the peak multiplicity. So this gives us our complete structural assignment for this compound. We're going to do some more examples on this, but I wanted to present this guided example and help you break down the steps to interpret a proton NMR spectra. We're going to be applying this process to the next few examples.